of time for those of you who haven't taken OR algorithms or a market design class to talk about the Gale-Shapley algorithm, which is the most basic form. It forms the basis of all the work that Al Roth and his co-authors did thinking about various kinds of matching markets. And it's really just, it's a really cool paper. It's one of those papers when you read it in grad school, I think it's like 5 pages long, and you're just like, excellent. That was, like, you feel very satisfied after you read it. And I think Gale died before he could get the Nobel Prize, but Lloyd Shapley won it in 2012. So the key piece here, and I want to step back if we think about the sections of market design, is typically most of the things that we buy and sell on a regular basis, that transaction involves money, right? So we go in and we decide what we're going to buy and we pay a certain amount of money, and the money sort of plays 2 roles. It decides who's going to get how much money, and then also who's going to transact with whom. There are actually markets, and this is one of them, or the residency match is one of them, and there are others, where prices for whatever reason are not used. Right, so like, for example, I don't know the whole history of this, but in medical residencies, the salaries are actually preset before the match occurs. And I believe the match got sued for wage suppression, because the argument was that if you let people freely bargain, the really good residents would make more money, right? But for whatever reason, residents set these things in advance, and you have other types of markets where I think for judicial clerkships, the salary is technically all the same. And so what you're really thinking about is the matching of judge and clerk. So what is so cool about this algorithm is you're thinking about a marketplace, and we're going to use the nice old terms. This is really fun if you're a female economist. We're going to be talking about men and women. So those are going to be the 2 sides of the market. And we're going to go through this algorithm and how you think about designing a centralized algorithm in a marketplace where you have, for whatever reason, you're not using money. All right, so we're going to have 2 groups of participants. I'm going to call them men and women. And they're going to care about their matching, right? So they're going to have preferences over the other side of the market. And preferences, for those of you who are in this class, you actually don't need a utility function here. What a preference is just going to be that, if I'm man, that's the end of the string of good markers. If I'm man M1, so the men and women are going to have subscripts, this just means that I'm going to have, preferences over the women, right? And so forth. So everybody in this market is going to have preferences over, the other side of the market. Okay. So we're going to have a set of men and a set of women, and each man can be matched to at most 1 woman, and vice versa. So what you're going to end up with is, the ideal situation is that each man and you're going to end up with people in couples. And you can also end up with people alone. So there's an idea of acceptability, which is that you're allowed to say, first the preferences are going to be strict, and then you're allowed to say as man 1 that I don't want to be matched with woman 0. I would rather not have a match than be matched to woman 0. So that's also an option. All right, so as I said, matching, you're going to end up with a set of tuples. And technically, you usually write, if someone's matched to themselves, what you'll just see is, man 1, man 1. This means that I didn't end up matched. And so the definition of stability in this case, and I really want to focus, a great way to think about it is that there's no man and woman who would prefer to run off with each other than stay with their current match. But technically, a matching is stable if in the matching, everyone is acceptable to their partner, right? So you don't have anybody matched to someone where they're like, I don't want to be matched to that person, I told you that already, right? And then there is no man-woman pair who would prefer to abscond rather than staying with the person that they're assigned to. And so if there is a pair that wants to run away together, this is typically called a blocking pair. All right, so any questions so far? Yeah.
So this paper, is this the one from like the early 1900s where it's just like 10 men and women, they want to get married? And
I think it might be the 60s, but...
So, is that the one though? It's like a very small sample size, right? Like 10, 20?
I think the theory paper doesn't, yeah, one of the things I really like about this area is all of the examples take like 2 men and 2 women, or 3 men and 3 women at the most. It's very cool. Yeah.
Is the definition of an unacceptable woman to the man only the last one in his list?
No, typically what you'll see if someone is unacceptable is that they're just not on the preference list. So you would see, like, suppose that there's 3 women and man 1 finds woman 3 unacceptable. You'll see, like, he prefers woman 2 to woman 1, whereas woman 3, right? So that's more, I think that's more typically what we see. All right. So here's a really simple example. If you have, you have 2 men and 2 women, you have man M and man M prime, and then you have woman W and woman W prime. These are their preferences, I won't go through them. And what you can see here is, this is one possible match. So you could assign man M to woman prime, and man M prime to woman W. But the problem with this, does anybody see why this is not stable? Yes, whoever just said that is right. Woman prime and man M prime are each other's first choices. Right, so if we assign them this way, these 2 would say, wait a minute, bye, I'm out. Right. And so this ends up being the unique stable match. Okay. So there's a question then about, suppose you have a market that looks this way, how do you find a stable matching? Right, we're looking for this holy grail of stable matchings, how do you do it? And this is where the Gale-Shapley algorithm comes in. It's also called Deferred Acceptance. And this is the algorithm that you use and gets used in various varieties in marketplaces of this type. And so the way that Deferred Acceptance works is that first, everybody sits down and ranks all their partners. So they say, okay, these are the people or the jobs or the women on the other side of the market. Here's my ranking of them. Just a quick question. If you're implementing this in life, what is one problem with what I've just said? What could be hard about writing down a unique ranking listing of everybody on the other side of the market? Yeah.
You don't know everybody on the other side of the market.
You don't know everybody on the other side of the market. You could have imperfect information about people on the other side of the market. In practice, this can be tricky, right? But in this case, useful abstractions. Men and women rank all potential partners. And the way the algorithm works is the following. So every man is going to propose to his first choice woman, right? So I'm going to go up, I'm going to say, I would like to be, man M would like to be matched with woman W. And so the women are going to look at the set of men who have said, I want to be matched with you, and they're going to pick the one they like the best. And so at that point, you're going to have a set of sort of tentative matches where the man proposed and the woman said yes, and then you're going to have a bunch of men who struck out, where either they proposed to someone who had a better option or they proposed to someone who didn't find them acceptable, right? So then those men who are not matched are going to go again and propose to their second favorite woman. And at that point, the women are going to say, okay, maybe I had this one from last round, and this new person's proposed to me, I'm going to pick the one I like the best, and then the men who are unattached let go. And so we work through the list of preferences until everybody's either gone through all the way or everybody has a match, right? So you go down your list, you propose to everybody, at which point you're going to have a set of couples and some unattached people, and this is the matching that you end up with, right? And so this is called the man proposing match, and there's also the women proposing match, which is the opposite, the women propose. Yeah.
How does time play into all of this? I know that you mentioned kind of you don't pay attention to it in stability, but to me this is a point in time, and as you're building your utility function, I assume that that's a variable somehow?
It is. It could be, this overlaps nicely with various forms of concepts in contractual completeness. Lots of people get divorced.
Yeah.
So that is one piece that is challenging, and so typically these types of markets don't take time into consideration, or if you do, they expect you to look forward and bake it into your ranking. Where if you're like, I like you more now, but I'm gonna like you more in 10 years, they expect you to sort of do that work ahead of time and say, on net, this is what I prefer. Yeah.
But like in some of the systems that we're focusing on, like decentralized ones, as opposed to, let's say, like residency matching, where there's a fixed number of medical programs and a fixed number of people who are graduating, these networks like grow over time, where the potential supply of matching on both sides changes. So like for that time question, like how would we handle that? Or
Right.
who will get sort of
So that's a great question. There's another area of research. So I think there's two different pieces here. So there's a question about what if my preferences change over time? And then there's a question of what if the market is changing over time? And for that second question, there's an area of research that is related to this, which has to do with kidney exchange, which is organ donation. And one of the things they think about there is that you constantly have people coming in who need kidneys, you have people who have kidneys, you have people who die. And so one of the things they study is how often do you run your algorithm, right? What is sort of the optimal point where, like, if you wait longer, you have a thicker market, but then people are waiting for organs. So like, what's the trade-off, right? So it's a really interesting question, and it's thinking about those dynamics are actually an active area of research, but it's a good point. All right. Yeah.
Well, because of the time steps though, doesn't the time step nature allow for the existence of possibly a lot of blocking pairs? Because like say you have a man and a woman, right? And they're each other's, like, let's say that they're not each other's first choice.
Yeah.
Then the next time step, the woman would prefer to be with that man, but maybe he would prefer to be with some other woman, but then that woman is his third choice, and had she known that he would strike out in the second round, they would actually be a better pair for each other than the woman being with, her second choice, which would be her third choice had she known the second man were available.
So I'm not 100% following exactly, but I think if the preferences are not changing over time, then this algorithm will take care of that. But I think it's very hard to play out those contingencies if you do have preferences that are changing over time.
Can I add on here? I think it's also, so economists like to also pick stylized examples like this, and I think it's helpful to not get too hung up on, right, we think of them maybe as lifelong partnerships.
Sure.
In many of the contexts where you actually see these types of algorithms applied, you're looking at the match for something that looks like a discrete contract. So we're gonna execute this 1 year of schooling or this 3-year residency, and then there might be another match after that, or different people participating the next year. So what I think what is maybe important to think about if you have a two-sided matching problem where both sides of the market are interested in who they transact with, that you think about what is it that we're matching on? How can we make this a discrete transaction so that people can go back to the market and match another time for their next trade?
Yeah, that's a good way to put it. And there is, you'll see when we get to sort of the extended work that work based on this has ballooned. And given pretty much any question you ask, I would not say no one has done it, right? There's a ton of stuff out there. Cool, so from a mathematical point of view, you might say, well, how do we know is there a stable matching in every matching market that looks like this? Right, like can we prove the existence of at least one stable matching? And the answer is yes. And the way you find that at least there can be multiple, but the way that you find at least one stable matching is by using the deferred acceptance algorithm. And the proof is really, really nice. Again, all these proofs are, they just make your brain happy. So first, because we're looking at a market with a finite, I don't think that was written down, but we're thinking about a market with a finite number of men and a finite number of women, the algorithm has to end, because at some point, you're gonna have to propose to everybody on your list, right? So it has to stop in finite time. And so you think about, okay, well, suppose that we run deferred acceptance, we end up with a tentative matching. Well, how do we know that this is stable, right? So let's take a man, this is man M, and he says, you know what? I matched with woman W, but I really preferred woman W prime. Well, he's already proposed to her, right? Because he started with his number one woman and he went down the list. So if he's matched to a woman that he prefers less than this woman, he already proposed to this woman, and she either found him unacceptable or she had a better option, right? Because that is why he got jettisoned and now is with this woman that he prefers less. And so because of this, anytime that a man thinks that they have a better option, that woman has already been proposed to by that man and has decided that this was not the better choice. They had a better choice given this setup, right? Yeah.
One question, this kind of refers back to his question about the blocking issue. So it's possible that two people, the man you said proposed to that woman initially, and she said no because she was hoping that her number one or number two, so let's say that guy was her number three, the number one or two is going to propose to her first.
Yeah.
And this thing goes on, and it turns out her number one and two chose other people first. And she ended up with he's number two, she ended up with her number three. So frankly, she's still his better choice of the remaining. In other words, if you were to offer this man to her now,
yeah,
she would take him.
So the thing is that a woman is never going to turn down an acceptable man because she knows that if she says yes to her third preferred man at the beginning, and then 3 rounds later her first man shows up, she's allowed to dump him and go with the later one. Okay. So that kind of speculation in this particular case.
I think we need to add that to the list.
It was on the previous slide, but yeah. That's part of how the algorithm works. And I think just keeping in mind, so when you look at the actual medical match, so we're talking about acceptance or rejection, but it's actually not the individuals who are seeing the match come to them and then accepting or rejecting at the time. It's all run on a computer. You just give your preferences, and the computer does the accepting and rejecting for you based on your preferences. Yeah. So it runs according to what the algorithm says you should do at that moment.
Fine. So in that particular case, clearly that part of the algorithm is great for the women because the women always end up with their best choice. So that man who was originally selected is now have to go back into the pool of the unmatched women to see if his next best choice is available. And what if the next best choice, so he constantly has to, there's a feedback loop.
The interesting thing here is that one of the things you can show is that if the men are proposing, they actually end up with their best possible stable matching. And you can go through, I won't do the proof of this, but if the men propose, you can have multiple stable matchings. I won't get into the math, but you can get multiple ones. The men get their favorite if they propose. The women get their favorite if they propose. And when the men propose, the women get their worst matching. Yeah.
So is this like that Black Mirror episode? So they have a whole algorithm using people and ended up.
What's it called? Something at the disco?
Acceptability.
There you go. Yes, actually. We were thinking there's a blockchain-based AI company in Pasadena that does avatars, and we're just thinking if we can put the blockchain-based avatars with Gale-Shapley, we can have that Black Mirror episode. So we're almost there. This is a joke. This is not a business thing. No one has actually done this. Right, and so just, again, I won't go through this, but the interesting thing is that if you're the side that gets to propose, you end up with the best of the stable matchings for you. And intuitively that makes sense, because if you're proposing, you're starting at your number one person, and you stop at the first time that you're starting and working your way down your list. And here's something, I think this is interesting, and I would be interested to know, for those of you who have come across this algorithm in OR or engineering classes, whether this is studied. So, the algorithm is a fantastic algorithm, but when you're thinking about how are people going to interact with this algorithm, one of the assumptions that is in the original Gale-Shapley paper is that I'm going to show up, I'm going to truthfully tell you everything that's on my list. And so a very important question to ask, and this is where I think it gets more into the economics, is are the users of this platform going to show up and truthfully report their preferences? And the answer is, and again, I'm not going to do the full proof, is that if you're the side that's proposing, yes, you're going to show up and you're going to be truthful. Why? Because you get to work your way down the list of your favorite people, right? Why would you lie and propose early to someone when there's someone you like better and you have that choice? However, if you're the side that's receiving the proposals, it is in your best interest to be untruthful, right? So you can imagine a very simple case where I'm a woman and there are two men who are going to be proposing, and I know that man one is going to, I prefer man two, but I know that he's my second choice. And I know that man one is going to propose to me, but I want to wait for man two. It might be in my best interest to say, even if man one is acceptable to me, I might lie and say that man is not acceptable to me. Because if I say that, then I can wait. So there are permutations where basically the women are going to find it beneficial to be dishonest about their preferences, because they don't have the power they don't get to propose. And so again, this is where this goes from OR into economics, and this becomes incredibly important. I'll get your question in 1 sec. So versions of this algorithm have been used in matching students to public schools. So they use it in Boston, they use it in New York. And so whether it is truthful reporting is in the best interest of the parents is important for a couple of reasons. So one, it's just easier to use an algorithm that's called strategy proof, where it's in your best interest to tell the truth. But also, when you have an algorithm that's not strategy proof, when it's better to be deceitful, you end up with basically socioeconomic differences in who knows how to lie correctly. So there have been studies of this. I believe it's the Boston match is not strategy proof, the one they use in Boston. And what you find is that really well-connected, wealthy parents understand the right way to lie to get their kids into the best schools, whereas parents who aren't as connected, who don't quite understand, will often go in and report truthfully, which is not the best option, and then given that other parents are being strategic, it makes it even worse, right? So thinking about, not only is my algorithm really nifty, but how do people interact with it is really important. Okay, there were hands, yeah.
So going back to our lesson the other day, this is where game theory comes in, right? Because now the preferences of the rest of the group make a difference for me as the woman.
Yeah, exactly. So this is, exactly.
And I guess the question is, does the strategy provability depend on how much information can be gleaned by the participants about the system, independent of the matching algorithm?
That's, you're nodding a lot.
No, I mean, that was okay.
Yeah. No, that's right. And so it's, if you think about the school example, there's a couple types of information that well-connected parents can get. One of them is which ones, there's a huge number of schools, which ones are the best, going back to, what about this assumption that everybody can rank everything? There's a lot of information that's collected by word of mouth about what your preferences should be. And then there's the piece which is, how do I play this algorithm correctly so that I get my kid into those good schools? So there's sort of two pieces of it. But yes, this is exactly where the game theory comes into designing markets like this. All right, any more questions? All right, we're doing enough time. All right, so yeah, this is, any last questions on matching? So I'm actually gonna do 2 for 1. I'm gonna talk about prices for a little bit and then wrap up the market design section. Yeah?
So in the residency matching kind of implementation of this algorithm, which group was the men and which was the women, or was it not so clear cut?
I think that the residents propose. I think that they decided to throw a bone to the residents and have them propose. But if you talk to people who go through the match, I mean, the match is beautiful and it still works like 20 years later, which is a testament to it, but there is a lot of, not all residents love the match, but I believe they do resident proposing. So you sort of end up with the resident optimal match.
I didn't
Yeah.
catch this in that specific example. What do they do with the people who are unmatched at the end?
It's actually something called the rural hospitals theorem. So one of the things you can prove is that in any stable matching, the set of unmatched people is the same. And the reason they call it rural hospitals is because those are the hospitals no one wants to work at. And so there have actually been some market designers who work on the medical match have started exploring how do you design various incentives because rural hospitals need doctors too. So how do you start to use a combination of immigration policy and matching and incentives to get people to go to those hospitals? Yeah. But yeah, you're gonna end up with most likely a pool of unmatched people, and they will be the same no matter what version of the algorithm you use. All right. So again,